All right, we got audio. Good. So as we talked about last time, the Suzuki reaction is a cross-coupling reaction between two parts. Both of them are sp2 hybridized carbons. One of them is an aryl halide, and the other is a boronic acid or a boronic ester. Some sp2 hybridized carbon can be vinyl or aryl, and then the boron is attached to the carbon, and these can be either OR groups or OH groups. And you have a palladium catalyst and a base, sodium hydroxide, and the new bond you make is that one between the carbon that used to be bonded to the halide and the carbon that used to be bonded to the boron. So in terms of like predicting products, it's pretty easy once you recognize it as a Suzuki reaction. All you got to do is make the new bond between those two sp2 carbons. The other thing you got to remember is if there's stereochemistry for the vinyl halide for the halide or for the boronic acid, it's preserved in the product. So this boron is trans to this methyl group, and in the same way, the methyl group is trans to the thing that replaces the boron. We talked about mechanism, and this isn't anything you would need to be able to predict, but I do want you to recognize and be able to call steps oxidative addition versus reductive elimination. We talked about how the palladium zero catalyst with 10 d electrons and 14 electrons total does oxidative addition with the aryl halide. The electrons in these metal X ligand bonds, 2 of them come from the palladium and 2 come from the carbon bromo bond. You go to something that's palladium 2, palladium now only has 8 d electrons. Where did the other 2 go? Well, 2 of them are now in one of these metal ligand bonds. Then you get what's called transmetallation, and this is a step that we're not worrying about in any mechanistic detail. We're not even thinking about arrows. All we're saying is the bromo gets swapped out for the carbon that's attached to the boron, and the stereochemistry of that connection gets preserved. And then lastly, there's a reductive elimination step where you can envision 2 of the electrons in one of these metal ligand bonds becomes the new phenyl group carbon bond that we make, and then the other 2 go back onto palladium, and that's reductive elimination. So in terms of that mechanism, I wouldn't necessarily expect you to be able to draw it out from start to finish, but if I showed you a step based on oxidation state, you should be able to say, yes, that's an oxidative addition step, or no, that's a reductive elimination step. Want to do just a little bit more predicting the products. One of the ways your text pushes you a little bit on synthesis questions with the Suzuki reaction is they'll have you actually make the aryl halide or the boronic ester. So just as a quick reminder and a review, making aryl halides is easy. You've done this before a ton of times, right? You could take a benzene ring and you could just do the bromination reaction and put the Br on. If you had some other functional group on it and you needed to get a particular arrangement of groups, supposing, you've got the other strategy of putting a nitro group on first, then doing the palladium catalyzed reduction of the nitro group to the aniline. And then this is the diazonium type chemistry that we learned, converting the aniline into the diazonium salt. And then once you've got that, you could use some kind of copper halide to replace the diazonium group with a halide. So a couple different ways to do that. That's just a review from things that you've seen before. The making the boronic esters is a little bit trickier, and so your text introduces a couple of ways to do that. First is to use an organo lithium reagent. So if I start with this aryl halide and I use lithium metal, this was how we prepared organolithium reagents back in the beginning. That's it's called halogen metal exchange, and the mechanism you don't need to worry about. But then if you take a boron reagent where the boron is attached to 3 OR groups, one of the OR groups comes off and is, excuse me, sneezing, replaced by the benzene, by the organolithium reagent. We don't necessarily need to push arrows here, although if you wanted to, you could. The electrons in the carbon-lithium bond go onto the boron and form a sp3 hybridized boron intermediate that's negatively charged, and then one of the OR groups comes off in a subsequent step. So that's not a complete mechanism, but it gives you an idea of what's going on. This reagent is then ready for the Suzuki reaction. The other option you'll see for making boronic esters is hydroboration of alkynes. And this is a reaction from 351. So you've probably forgotten it, but since you've got an ACS exam coming up, this is a good time to review that kind of thing. Here is a hydroboration reagent. It's got a BH bond and then 2 OR bonds. This is one that your text uses, and it is a real reagent that people use. It's mostly designed to freak you out. You look at it and you're like, I have no idea what that does, until you recognize these are OR groups, and that is a boron hydrogen bond. If you remember from 351, hydroboration involves pi electrons from the alkyne attacking the boron. At the same time, the hydride, the BH bond, which is already polarized towards the hydrogen, because hydrogen's more electronegative than boron, attacks the more substituted carbon. You get a product where the boron reagent, which we'll just abbreviate like this, and the hydrogen get delivered to the same side of the alkyne, and the hydride gets delivered to the more substituted carbon, because in the transition state there's the hydride carbon, the bond between carbon and hydrogen isn't quite as formed as the bond between carbon and boron. That leads to a buildup of partial positive charge on the more substituted carbon where it's more stable. So this is a great way to get a vinyl boronic ester simply by hydroboration of an alkyne. All right, so let's show you a couple of predict products from straight out of practice problems in your text. So here is an alkyne, and these are real examples. If you look at the structure here, those branching methyl groups tell you they're trying to synthesize something that's kind of like a terpene. There may have, I can't remember whether there was a pi bond there or not, oh well. So they use the hydroboration reagent that I just told you about. That's going to preferentially react with the alkyne. With the boron here and the new hydrogen there. And notice that the stereochemistry here between is E, that is the two high priority groups on either side of that alkene are trans to each other. And that stereochemistry is going to be preserved in the product. The next reagent is this vinyl halide. I should have said at the beginning that the Suzuki reaction works fine for vinyl or aryl halides. as long as they are sp2 carbons. And then you need that palladium catalyst with the base. And at this point, you're gonna, and recognize that in this Suzuki reagent, the two high priority groups on either side of the alkene are also trans to each other. So we're simply going to couple the carbon that was bonded to boron to the carbon that was bonded to bromine, and we're going to keep the stereochemical relationship about each of those double bonds the same. So here's the orange carbon that used to be bonded to boron. The new bond's got to go there so that this double bond can be Z, and then here, E, sorry. And then here is the carbon that used to be bonded to bromine. Here's the double bond. The carbon that was bonded to bromine also had a methyl group on it, and then the other methyl group was here. Okay? So that's all there is to it. Maybe one more example using an alternative way of making a Suzuki reagent. And there, sure, why not? This is a review. So we'll start, salute. All right, so the problem in the text actually doesn't start here, but since you guys are interested in reviewing stuff previously, how do I get from benzene to this? Very, very carefully, all right? Okay, well, first, do I know how to put a bromo group on there? Okay, that's easy. What about an oxygen? I know how to do that, but that's a little bit harder. Do you remember what the chemistry is? Got to make that diazonium thing? Yeah. So probably doesn't matter in what order, but let's imagine first we do the bromination. And then second, we do the nitration, HNO3, H2SO4. Then we reduce with palladium to get the aniline. Then we do the diazonium thing. We convert the aniline into the diazonium group. That would get us here. Then we could add hydroxide to get the phenol. At least this is how your text does it. And then we could add a base like sodium hydride that would deprotonate the phenol, and then we could add methyl bromide to get that molecule. Some of you are thinking, why didn't I just use methoxide here? Would that work? I think it would. Okay, so now you've got the aryl halide. I want to turn this into a boronic ester. So the strategy is to use lithium. That's going to do halogen metal exchange on the bromo to give me this organolithium reagent. And then I will add the boron reagent to convert the organolithium into the Suzuki reagent. OME means a methoxy group. All right. Then here is the coupling partner in the Suzuki reaction. Oops. And a Suzuki reaction is a great opportunity to learn to ignore details that don't matter and focus in on what does. You may look at all of that and you're like, why? What's the point of all of that? Well, they were clearly making some molecule for some purpose. But all you need to do is identify the one that's bonded, the carbon that's bonded to the bromine, and it needs to be sp2 hybridized, and then the carbon that's bonded to the boron, and then you're simply going to couple them together. So predicting the Suzuki product is easier than you might think as long as you remember what the Suzuki reaction is. This is an example of a linkage between two benzene rings. That's called a bi-aryl linkage. And those can be kind of interesting because if you make a model, if you were to lay it flat, the protons on the benzene ring here are going to start bumping into the protons on the benzene ring there. There's going to be steric clash. So those two benzene rings actually twist out of plane with respect to each other. And you don't want to know this, but sometimes there's stereochemistry associated with that. Sometimes there's something called axial chirality, which should scare you a little bit, but you won't have to really deal with that. So, all right, that is the Suzuki reaction. So last one. There were others, but we're not going to get to them in this chapter, and I can tell you're real broken up about that. But all right, the Heck reaction. What the heck? That actually is the guy's last name. So he didn't pick it. So the Heck reaction is also between an aryl halide and a vinyl halide. So that part is very similar to the Suzuki reaction. But the difference with the Heck reaction is the other partner can be just an alkene. Well, it needs to be, it's an alkene with nothing special on it other than perhaps an electron withdrawing group. In the Suzuki reaction, you notice that both partners had a special group that you could identify to know which carbons were going to get attached to each other. The Heck reaction's a little bit more complicated because we're going to couple the sp2 carbon from the aryl or vinyl halide with one of the two carbons of the alkene. The alkene is usually mono-substituted, doesn't have to be. Most of the examples from your text, it is. The other thing is it's usually the terminal carbon of the alkene that gets functionalized, but not always. It can be the other one too, so you just sort of have to watch for that. If you're predicting products, certainly it's more reasonable to couple this atom, but if you're looking at products and saying which of these is the correct product for a Heck reaction, you may have to try to anticipate either of the two carbons being involved. So the new bond is going to go between the orange carbon and the blue carbon. Notice that on the side of the blue carbon, because we're putting a new group here, we're suddenly going to have stereochemistry, and where there wasn't any to begin with. And the preferred stereochemistry is trans. And I'll show you a reason for this when we talk about the mechanism. The Heck reaction was discovered in and around the same time that the Suzuki reaction was discovered, and like the Suzuki reaction, it is catalyzed by palladium. The conditions Professor Heck used were palladium acetate, which if you look, I'll draw what a palladium acetate complex looks like. You've got palladium bonded to basically two carboxylates. OAC is acetate. The ligands, if they left, would be like that. it's a neutral complex. What's the oxidation state of that palladium? Why is that chair sitting there? That is weird. Just looking at Jens and saying that I can't see Jens other than his torso because of the chair. Well. I feel like that's the timeout chair. Like somebody's going to go to timeout and have to sit in the chair. All right. Any idea what the oxidation state of that palladium is? 2? +2? Okay, how do you know? Both of them are negatively charged ligands. Yeah, the acetate ligand is what's called a bidentate ligand. It binds the palladium on 2 of its atoms. On this side, these 2 electrons are just lone pair electrons on the carboxylate oxygen. On this side, these 2 electrons are the negatively charged conjugate base of acetic acid. So acetate has an L ligand here and an X ligand there. But overall, if they left, it would be -2. So yeah, this is palladium 2. Palladium normally has 10 electrons, so this is a D8 metal with 2, 4, 6, 8. That's a 16 electron complex. Now, that's what you start, your source of palladium in some of these reactions is doesn't have to be the same as the catalyst. Sometimes people actually build the catalyst ahead of time and then put it into the reaction. Other times they just dump in the reagents to make the catalyst in with the reaction and things work out. And the Heck reaction is one of those. So you start with palladium 2. You need some ligands for palladium, and the ligand is a phosphine. And so it's really weird. I mean, it's not that weird. It's triphenylphosphine only in addition to the benzene rings. Each of the benzene rings has a methyl group on it. And people have done a lot over the years changing the identity of the phosphine ligand to improve reactivity and selectivity in palladium complexes. You're not getting the backstory on why they chose that instead of triphenylphosphine, what's with the additional methyl group. Unfortunately, the way your text writes this is PO-tolulyl-3. The O stands for ortho, the tolulyl stands for this group that's toluene, basically. That's what a benzene ring is with the methyl group attached to the phosphorus. So that is the ligand. You are welcome to write it as PR3 and just move on from there. But the identity of the phosphine ligand does influence the reactivity of the catalyst. Okay. So with that in mind, you already, and then you need a base. And that base is usually triethylamine. So you'll recognize the Heck reaction as distinct from the Suzuki reaction for 2 reasons. First, in the Heck reaction, one of the partners is just going to be an alkene. And that alkene will usually have an electron withdrawing group attached to it. The other way, whereas the Suzuki reaction, the other partner needs to be, in addition to the aryl or vinyl halide, needs to be a boronic ester. The other difference is for the Heck reaction, the reagents are different. Instead of palladium 0, your reagent is palladium 2. You have a different phosphine ligand and you have a different base. So you'll have to work to recognize those reagents. Flashcards might help you with that. So with that in mind, let's just do a few sort of predict products. And then we'll deal with the mechanism. All right, so the fact that one partner is a vinyl halide, whereas the other partner is just an olefin, gives you the clue that it's a Heck reaction, and then the identity of these reagents tells you that it's the Heck reaction. In the Heck reaction, you're simply going to couple the orange carbon with the blue carbon, remembering that for simple olefins or alkenes like this, you couple with the less substituted carbon. In more complicated cases, you want to be on the lookout for the possibility of either one. Here is the product. There's the new bond between the orange carbon and the blue carbons. And then selectively, we go for trans stereochemistry on, because we've changed a monosubstituted alkene to a disubstituted alkene. Selectively, we go for the trans configuration there. So the Heck reaction is a interesting and useful way to make a diene. And actually, if we scroll back, the Suzuki reaction also can be used to make a diene. So, just connecting to things that you learned before in 351, what can you do with dienes? As opposed to, I suppose you can draw help. I'm dying. Write that on your exams. Need to make him a little bit more anthropomorphic, but that's okay. All right. What do you remember? What do you do with dienes? There was one from 351. Diels alder. Do you remember that one? No. So, you could be prepared for a synthesis kind of question where you would draw this diene in its S-cis configuration and then add some kind of dienophile. The dienophile is usually an electron deficient olefin. And then you would end up with various potential products, and it may be worth your time to go back and just check. And I'm clearly not writing a Diels-Alder question on my final exam, but I can pretty well guarantee that it would be on an ACS exam because that's an important reaction. So you may want to go back and review what you learned about the Diels-Alder reaction, especially about the stereo specificity of it. Notice that the two groups on the dienophile end up cis to each other in the product. Notice that the two groups pointing outward in the S-cis conformation of the diene also end up on the same side. That's required, and then you get two different diastereomers where the substituents on the diene that we're pointing outward are either on the same or opposite side as the substituents on the dienophile. And of course, if you make molecules that are chiral, you have to get both enantiomers. So that's just a fun review. Fun or discouraging. All right. All right, so I think you should go back and do some practice problems if you haven't already in the study guide on predicting products for the Heck reaction. Yes?
I asked just about the Diels-Alder.
Yeah.
Like endo and exo, which one would be endo, which one would be exo?
Oh, I always get this wrong. Endo and exo refers to these two diastereomers which differ in the orientation of the groups on the diene ophile and the groups on the diene. Technically, the term endo and exo was most often used for dienes that look like that. And then dienophile could be sort of whatever. And in the Diels-Alder reaction, you would get, the product of a Diels-Alder reaction is always a cyclohexene ring. You would get two potential products, one in which the substituents on the dienophile were on the same side as this bridge on the diene. And if that was true, we would call that exo. And then the other was where the substituents on the dienophile were pointing down relative to the bridge on the diene, and that one we called endo. You can assign endo. Endo is about the relative relationship between those groups. You could potentially assign endo versus exo here if you envision that these protons in the diene are in the same position as that bridge, but people don't do that so much. But yeah, if you're using cyclopentadiene, then choosing endo versus exo is, exo means the substituents on the dienophile are on the same side as the bridge, and endo means opposite. Okay, what else? Yeah?
And like, endo is usually preferred, right?
Endo is preferred usually, yeah, for various reasons, but that's the standard result of the Diels-Alder reaction. Okay, others? Okay, well, one last thing you don't want to know, but I'm paid to tell you, so what are you going to do? And that is the mechanism of the Heck reaction. So it involves oxidative addition and reductive elimination, but it also involves some new steps that are kind of weird. And I just want you to be able to recognize the oxidative addition and reductive elimination steps. Now, the interesting part of the story is that even though Professor Heck used palladium-2 as the starting material, palladium-2 is not the active catalyst. Instead, it's palladium-0. So what ends up happening, and you don't need to understand how this happens, but basically one of the phosphine, some amount of the phosphine ligands, one of the phosphine ligands actually ends up reducing the palladium from palladium-2 to palladium-0. That can happen because phosphorus makes pretty strong bonds with oxygen. You don't necessarily need to know that, but it was an issue that was sort of confusing to me as I first started teaching this stuff. I've actually never run a Heck reaction, which is kind of, I don't know, embarrassing. If you want to know more about it, you can talk to Dr. Michaelis or Dr. Castle or Dr. Peterson or Dr. Andrus, who've all done this kind of stuff before. So the first step of the Heck reaction is very similar to the first step of the Suzuki reaction. You've got a D10 metal that's in its 0 oxidation state with 14 electrons overall. And let's suppose, if it's okay, let's do this, the reaction we've already shown here. Here is the halide, and here is the benzene ring with the OMe group. And the palladium is going to do oxidative addition with that sigma bond. We're going to, the palladium is going to insert between the bromo and the carbon. We're going to end up with an intermediate that looks like this. Recall that one of the metal ligand bonds comes from electrons on palladium, and the other comes from electrons in the bond between carbon and bromine. You really can't tell which is which, But now palladium has two X-type ligands. It's still neutral, so this is palladium 2 plus. It's a D8 metal, and this is a 16 electron complex. All right, so far that's just exactly the same as the oxidative addition step of the Suzuki reaction. What happens now is really kind of interesting. Note that the complex is 16 electrons, so it's still got space for another ligand. And here's where that alkene comes in. So we're going to draw the alkene. It's going to come in, and it's going to bond. The pi electrons of the alkene are going to sit down onto palladium, and the pi electrons themselves are going to coordinate palladium. Now that's really hard to draw, in the sense that when we draw a bond, we typically mean, hey, there's 2 electrons in this bond between one atom and another atom. With pi electrons serving as a ligand to the metal, what we really mean is the 2 atoms involved in the pi bond are both interacting with the palladium, and the 2 electrons in the pi bond are forming that interaction. We can't really do something, we could if we wanted to do something like this, but that's a lot of dotted lines and it seems kind of confusing. So what we do is we just make sure we know that the pi bond is there, and we draw a dotted line here to indicate that those pi electrons are coordinating the metal. At the same time, you've got still the carbon palladium bond, the bromo, and then the 2 phosphine ligands. Sorry, those are R groups. So now this is still palladium 2 plus. It's still a D8 metal, but now we're at 18 electrons. We've hit the limit. This is coordinatively saturated. All right. So what happens next is the stage at which we make the new bond. I'm going to label electrons just to have an idea of what's going on here. This is a new step, and I don't necessarily expect you to be able to predict or even recognize this step, but I do want to talk our way through it. This is called migratory insertion, which is kind of crazy. What happens is the bond between carbon and palladium migrates here to form a new carbon-carbon bond, and then the blue electrons in the palladium, in the pi bond, actually go to form a sigma bond between this carbon and palladium. So when we're done, I did that wrong, didn't I? Nope, that's fine. So when we're done, this group has moved over to form a bond with this end carbon on the olefin, and the electrons in the pi bond are now bonded to palladium. We're still at palladium 2. Still a palladium 2 complex. It's now back, it's still D8 electrons. It's now down to 16 electrons total because one of the ligands moved off of the palladium. All right, so this is notice that we've made a sigma bond, but we lost the pi bond. We made a new carbon-carbon sigma bond between the terminal carbon on the olefin and the carbon that was bonded to palladium. That's our new bond there, but we don't have a pi bond, and that's what we need. So the last step is well, not quite the last step, almost the last step, is a unique one. And again, it's not one that I expect you to know about or recognize it, but it's important for this reaction. This is called beta hydride elimination. And it's not that different from something you saw before with NAD plus type oxidations. You've seen electrons kick down to kick off a hydride, and the hydride's immediately received by something else. What happens here is the electrons in the carbon-palladium bond kick down to form a pi bond, and then the hydride gets kicked off and delivered to palladium. The process here is, and there's a reason for it, but we don't really have time to go into it. It's selective for trans because the palladium has to be on the same side of the molecule as the hydride for this to occur, and the most stable conformation is for this phenyl group and this cyano group to not be eclipsed with each other, but to be sort of on opposite sides of the molecule. So that's the point at which we get our product, which as we drew above looks like this. And then what we're left with is still a palladium-2 species, where now the two things attached to palladium are hydrogen and Br. If we do reductive elimination, we form a new HBr bond, and then palladium gets the other electrons and returns to palladium 0. And then the purpose of that triethylamine base is to soak up the acid that forms in the reductive elimination step. And that gives you this ammonium salt, and that moves the reaction forward. But, you know, the key question is, could you for the mechanism, the migratory insertion and the beta hydride elimination are interesting, they're essential for the reaction. They're not explained in the text, so I wanted you to at least have me talk you through it so you could have an idea of what's going on here instead of just seeing this as a magical box that does the chemistry. But I do think you have enough of a basis in this to recognize this as an oxidative addition step and this as a reductive elimination step. All right, questions about that mechanism? Okay. End content. Now questions. I think you're voting with your feet. I think you just want to get the heck out of here, which is, I think, fine with me. Yes, go ahead.
Okay, you might have already mentioned this, but will the final be from terpenes to this?
Will the final be from terpenes to this? My final is cumulative and comprehensive, but I've made no effort to evenly cover all of the subjects. If there's things I haven't tested on yet, then they'll probably be on the exam. Other things are things from earlier in the semester. You're not going to know. Your purpose in taking the exam is to demonstrate to me that you've mastered OChem, so I don't really have a problem giving you a test that doesn't talk about all of the things in OChem. You may end up studying things that are not on the exam, and I'm okay with that because, again, my goal is for you to know OChem, not to memorize what's going to be on the test. That being said, you will probably feel like the exam is more emphasizing the latter half of the class. I'm okay with that because everything we've done is really an illustration and demonstration of earlier reactions. Okay, what else? Yes?
With glycolysis, do we need to know the mechanism of every step?
Glycolysis, do you need to know the mechanism of every step? I believe the one that we didn't do was the phosphoglycerate mutase step, where the phospho group moves over from the 3-hydroxy to the 2-hydroxy. Other than that, no. Yeah, you gotta know. Yes?